Okay, let's go ahead and get started. Hello, folks. This is Roger Brewer with the Hawai'i Department of Health Hazard Evaluation Emergency Response Office. So thanks again for joining today. Have a good group. And what I want to go over today is updates to Hawaii's site investigation, design, and implementation guidance, what I started calling and other people started calling risk-based site investigation. So our guidance, say over the last 20 years, has evolved pretty much the way this slide looks. It's really packed with information, a lot of field experience, laboratory experience, and such. So I think you're calling it Hawaii's guidance now is a little bit of a stretch. There's been a lot of input from people on the mainland. Also, some of you know I've been doing quite a work in China the last several years. Also, our guidance is being used in other places. I know in Vietnam, in Japan, I'm pretty sure Korea, other parts of the Pacific. And I've talked to people in Europe and in South America too. So I'm more of a compiler more than a researcher. So I'm just compiling everyone's ideas and putting it into this guidance. First of all, today I'll go over a real quick note on previous updates to our guidance. And then purpose of the 2023 updates, go over some of the highlights. I'm not going to go into much detail at all about individual sections. It's more just to give you an overview of the updates. And I want to put in a case study, which is hopefully you'll find interesting. Like, does this really work in the field, especially when you have to think fast on your feet? Then it will end up just talking about potential future webinars. The last updates to the guidance, here we're focusing on sections 3, 4, and 5, were done in 2016 through 2021. Our first guidance was published around 2009. We actually started doing looking at decision units and multi-increment sampling and theory of sampling in 2004. So we're approaching our 20-year anniversary. So in section 3 of the previous guidance, discussed systematic planning of environmental investigations. Section 4 focused on sampling theory and the collection of multi-increment samples. Section 5 was more of a lot of tips and field experience, focused on field implementation. Starting off with site preparation. You really need to see the site before you go out there. Demarcation of decision units, what kind of tools you would use for different types of scenarios of collecting soil samples. And then also section 6 of our guidance addresses investigation of surface water and groundwater. We incorporated concepts of theory of sampling into that, decision units and multi-increment type samples in 2021. Section 7 of our guidance discusses testing of indoor air. The indoor air folks have known what they're doing for quite a while, and also incorporating concepts of decision units and such in soil gas investigations. We did that in 2017. 2017, we, John Peard and I and a few others gave a 6-part webinar on the above topics. You can see the different 6 parts here. They're still very pertinent, and they're posted to our web page. But one thing several people pointed out is we're preparing this guidance, and it's really good if you already know what you're doing. As someone said, you have some basic idea, but it's difficult to start off with. The professor I talked to on the mainland at a university wanted to use our guidance document as sort of a textbook, but he said too it needed to be rearranged so it in more of a textbook format. Some way it made it easier to teach, because there are a lot of pieces and parts in all 3 sections, kind of mixed. So that's what we did in 2023. We just published it. I've actually been working on this for the last several years. And in 2016, if you kind of skip down somewhere the photographs are, I was chairing a session on theory of sampling and multi-increment sampling and such with Dina Crumling from US EPA at Patel Conference in California. There's a group of Chinese in the room from the Chinese Academy of Sciences. After the session ended, and I was out in the hallway, and they came by and we started chatting. They are very interested in trying to figure out how to apply our guidance in China, because it was starting to be there a Superfund boom. Things they still are booming in China, cleaning up contaminated properties. So we talked about it for a while, and then they invited me to go to to China, which actually I had moved here from China 30 years ago. I was curious to go back, and they actually were based in the same city where I used to live in Nanjing, China. So over the last 5 or 6 years, I've been going back and forth. We translated Hawaii's original guidance into Chinese, and then started rearranging it there. And one thing that they pointed out there, and other people pointed out, is that you need to really think about who's reading, who your audience is. So they said, think about it as some people, they have 5 or 10 minutes. They just need a very quick overview of what you're talking about, just semi-technical. That was part one. We did this by developing up some fact sheets we'd look at. Also, the second part, you have some people, they have an hour or two. Maybe they're the managers of an environmental company. This is all kind of new to them, but they have a decent technical background. So we need to present this whole approach as an overview, an hour or two, maybe 30, 40, 50 pages, but still kind of like with the fact sheets, lots of pictures and shots, not a whole lot of details, but a broader perspective on how it works. This is the new section 3. It's an overview intended for people who have an hour or two just to review it, give you a general idea. And then there's part 3. Those are all the details. And it's a series of, we're up to 17 appendices now on all the individual topics you can think of to deal with this, from theory of sampling, how to collect surface samples, subsurface samples, VOCs, test for those, how to process samples at laboratory and such, and we'll look at that. So we did that over the last 5 or 6 years in Chinese. It's actually the original version of this was in Chinese, and I translated it back into English with quite a bit of help. And that's what you're seeing now is the 2023 updates to the TGM in sections 3, 4. And then section 5 now, which used to be for field tips, is just reserved for future use, probably for something like DUMIS for UST sites. So that was the motivation for updating this guidance, make it easier to flow through for different audiences. And now with these appendices, we can take them out and update them, one at a time as we need to without having to update the entire document. This on the bottom left-hand slide here, that me and this other guy, that's Dr. Sung Jing, it's actually the picture of the first multi-increment sample ever collected in China. I think that was 2018 or so, 19. So first, a quick look at the fact sheets. So fact sheet number 1, again, for people with 5 or 10, maybe 15 minutes, to just get a general idea of what this whole process is. And it starts off with, what is DUMIS? And there's a lot of pictures and basic questions, such you can see here, taken from the fact sheet. This is in Appendix A of the update. Then second question, how is DUMIS implemented in the fields? This is decision unit multi-increment sampling methods implemented in the field. So very basic, review the site history, develop the site investigation questions. That's a key part to any investigation. We didn't really think that much of in the past. Then designate your decision units, collection of samples. Step 3, then you collect a representative sample of a decision unit. We've seen a lot of guidance in the past, including some I worked on. It just said kind of blankly, collect a representative sample. We're representative of what? So we're a lot more specific on that now. In step 4, after you collected the sample, a lot of time in the field, then the laboratory processes it and analyzes it. And it emphasizes there they have to do that very carefully. You don't just reach in a jar or a bag and take out a pinch and test it. Then you review your data and make decisions. That's it, gives a basic overview. Then why are DUMIS sampling methods necessary? This goes into the background and traditional ways we were collecting samples using discrete samples, collecting a random handful of dirt from one place and having the lab test a random pinch of that. Discusses some of the problems with that approach. And there's some references for where I can get more information. That's the fact sheet, quick introduction for people. Then as this is going on, there are other fact sheets being added. One of the consultants here in Hawaii, Kimberly Kim, her group put together a fact sheet for responsible parties. And she was saying, that RPs don't have time to spend 5 or 10, 15 minutes trying to figure out what's all in this fact sheet. For them, a lot of times it's just time and money. So they put together a fact sheet. We modified it some for inclusion in our guidance. Just gives different options. So time and money, and it's kind of you can pay me now or you can pay me later type discussion. So option 1, if you just want a quick and cost-effective screening of your site, let's say it's a commercial site or something, we're divided into big DUs, kind of based on how the site was used currently and in the past. Then you'll probably just collect some surface samples to get a general idea of what's there. A lot of times, especially here, you're looking for contaminated fill material or something. That's okay for a lot of sites. Maybe you get a developer, someone hasn't bought the property yet, but they want to get some general idea before they start in that process. Option two, you want to minimize restrictions on the property. So you might divide the property up into smaller areas for testing, maybe equivalent, say, our default residential reuse areas of 5,000 square feet, maybe half acre, depending on the site or something. So you get a little bit better idea of what's going on there and if you'll need to potentially impose any restrictions on use of the site. Then option three, it would be dividing up the site into more detail based on known or suspected source areas. This is more to optimize remediation. So you can get in, characterize the site, clean it up, and get out. And this is really useful, I think, for RPs understanding how this process could get drawn out. You start finding contamination, but you've gone with a quick and kind of cheap screening up front. And included in this fact sheet, some tips for adapting the sampling plan as the processing is moving. So it's really useful. I like these type of practical fact sheets. The third fact sheet we're working on, I've been for a while. Hopefully I'll get it done by December. And this is getting to be more and more of an issue, is sampling roadway and construction debris. And there is actually a case study in Appendix C that discusses how to do this. But this, again, you start back, what's the question? So if you're going to recycle asphalt or recycle concrete, and first thing you need to know if lead or PCBs in the paint or the sealant, the caulking or whatever, does it pose a potential health risk? And especially, say, the yellow paint on roads, some of that can be 30% lead. Our office would consider that an attractive nuisance. So all ground up, your concentration of lead might meet our action level of 200 ppm. If you have these little yellow shiny pellets in somebody's driveway where they bought recycled asphalt for gravel, then that gets to be a problem for children and such. So to discuss that, how you have to remove paint and sealants and such from buildings and asphalt if you want to recycle it. Or if you want to dispose of it, then you're looking at the question that would be what is the concentration of lead or PCBs in the building material as a whole? In that case, if you ground all this asphalt up, what's the concentration of lead? If you took a building and ground it up completely, what's the concentration of PCBs in the building now? It's probably well below any TSCA limits. But in this case, you would collect multi-increment samples, ideally, especially in buildings before you demolish it. As I've learned myself out in the field trying to collect samples from concrete debris. And you'll collect the sample through the entire thickness of material. That's getting to be a bigger and bigger issue and something we want to get a fact sheet out. But there is a case study in Appendix C. So those are the fact sheets. In section 3, again, this is intended for people with an hour to maybe the owners of an environmental company or a senior project manager who's spending most of their time just dealing with the business and such, doesn't have a lot of time to get into the details. So spend an hour or two or something. This section is intended to give a general overview of the site investigation design and implementation process. So it starts off with just discussing the application scope, the scope of the site investigation design, give some terms and definitions, things in red here to sort of highlight. It discusses the systematic planning process. So you're no more going out to the field, grabbing a sample, and let's see what we find. You want to be very systematic about it so that you can sort of get in and get out of a project. It discusses what decision units are and how to designate them in the field. Again, not a lot of detail in any of these, just the basic ideas. How to develop sampling analysis plans and ultimately be preparing site investigation reports. How to characterize decision units, collecting samples. There's a short discussion on what happens to the sample after it's collected in the field at the laboratory, how they should process it and test it. And then a discussion, especially emphasizes on the data quality evaluation, the usability of the data and how the data can be used for decision making. So this should be useful for people to get a general idea. Look at a few of the highlights from that. Systematic planning. A lot of this section is actually cut and paste from our existing guidance. So you see that these 9 or 10 steps to systematic planning here, same thing as we had before. There's something at the top Chuck Ramsey's always been emphasizing, and I still argue with myself and with him about it, but it's quite true. There's only 2 reasons to collect a sample. So before you go out in the field to collect a sample, think of why you're doing it. There's only 2 reasons. You're either collecting the sample to assess risk, or you're collecting the sample to optimize remediation. Again, no more just grabbing a sample. Let's see what we get, and thinking about it afterwards. So step 1 is where you state the problem, draft your conceptual site model, develop your investigation questions. Why am I here? Now, step 2, identify objectives and contaminants of potential concern. Step 3, identify data needs and uses. Step 4, you define your decision units. Step 5, develop decision unit statements. It's what you're going to do with the data after you get it. You don't decide this after you get the data. Develop these statements beforehand. You need to develop your sampling plan. You go out and collect the samples. Evaluate data usability, data quality. Identify any potential environmental hazards, as we call them here, for example, using our environmental action levels. You refine your conceptual site model. Do we need to go back to the site? Hopefully not more than once again. Then recommend additional action. And then in our office, you would prepare an environmental hazard plan that just summarizes what you found and what the potential concerns are. It gives readers a quick overview of the process. Section 3 of the update 3.3 discusses decision unit designation. Now, this more detail is provided in Appendix C of the document. That's in Section 4. Decision unit, if you're not familiar with this term, is just the area and volume of soil or whatever you're dealing with that's in question. So again, only 2 reasons to collect a sample: assess risk or optimize remediation. If you're assessing risk, lots of photos, pictures in the overview section. On exposure area DUs, it could be a playground, a soccer field, a commercial area, or some areas where construction workers or landscapers are working. For optimizing remediation, you're trying to draw a line around pockets or areas of heavy contamination that could cause, you suspect ahead of time, could cause risk issues. And then you have other types of decision units, boundary areas. We're trying to define a clean boundary around some source areas. It discusses subsurface decision units. The same process as the surface, you just have to go through soil, or if you're dealing with sediment, through a layer of water to get to the targeted soil. There's a quick overview of exploratory pits and trenches and boring DUs, where it's just not going to be practical to put in 30 or 50 borings, but you need to get an idea from single borings what's going on. And it's also sections on excavation DUs, stockpile DUs, just general, very basic ideas how you collect samples from stockpiles and testing clean fill material. And then a short discussion of set decision units for sediment. Again, there's more examples of these in Appendix C of Section 4. Section 3.6 of the overview then gives a short overview of how you characterize this volume of soil, volume of sediment, and whatever by collecting a sample. And as more details on this, it directs the reader to Appendix D and then to topic-specific appendices. There's a brief overview of how multi-increment samples are collected. So you define your decision unit. As a default for soil, you want to collect 1 sample from that area and volume of soil for about 50 points, maybe more if you have something like PCBs or lead-based paint chips and things. Maybe less. You're kind of taking a chance when you get less than that. And it's a discussion of collecting samples then of surface soils. More details go to Appendix F. Subsurface soils, more details go to Appendix G. And then still in Section 3.6, it's a discussion of how to collect samples or how samples are collected from excavations and stockpiles. That's more details go to Appendix H. And then collecting samples to test for volatile contaminants. That's something we need to have a separate webinar on. More details go to Appendix I. And then how to collect samples of sediment. More details go to Appendix J. I think this does a pretty good job on giving the basic idea of how site investigations are carried out, and then just directing the reader as needed, or other people maybe they work with, to the individual appendices for more details. And for assessing field sampling quality control, more details here in Appendix L. This discusses how replicate samples are collected. So how do you know that that 50 increment sample you collected from a DU is actually representative? If you go back, let's say someone else goes back in the future and retests that same area, are they going to get the same answer pretty close to it as you do, which you hope they will if they collected the sample right. Otherwise, you could have some liability issues. So it gives a quick overview of the need for and basically how replicate samples are collected in the surface as well as the subsurface. The 10% of your decision units you collect 2 additional samples from, and then you compare the data, A, B, and C, as you see here. And then you would have divided your decision unit up into different cells, and you collect an increment from each cell. Instead of just 1 increment, you would collect 3. So all your A's get combined into a sample, your B's get combined into a second sample, your increments from point C gets combined into a separate sample. Do the same thing in the subsurface soil. Problem here is you have to use a core. You see a direct push core, so your increments are really big. So now you can't send that entire increment from DU layer 1. If you combine 30 of those, it's going to be way too big to send to the laboratory. So you have to subsample it in the field. That introduces another type of error into your sample data. How do you know you subsampled that properly? So in 10% of your DUs where you're collecting subsurface samples, you're going to subsample that core 3 times and prepare 3 different samples and then compare the data. Just give you an idea of how good of a job you did subsampling. That's quality control there. Then section 3.7 gives a quick overview of what happens to those samples now that you've collected them. Sent to laboratories. They're going to be air dried, sieved, and subsampled for non-volatiles. Volatile compounds, you'll deal with methanol and something else. Then the lab's going to spread this out, and they're going to collect a small subsample of that. Typically, these samples weigh 1 or 2 or more kilograms. They're going to collect a sample, minimum mass, at least 10 grams, maybe 30. We'll talk about that in a minute. And they test. That's what they actually analyze. Well, how do you know they did that properly? But they're going to subsample 10% of the samples 3 times and then compare the results from that. So following this process, then sample data you get from laboratories is going to be representative of the sample you collected, and the sample you collected is going to be representative of what you targeted in the field. I've been meeting with a lot of mining sampling statisticians from around the world for the last several years. One thing they continuously point out is for unground, say soil or any particulate matter less than 2 millimeter size, then they strongly recommend you collect a 30-gram subsample for testing. That's the only way you can reduce their lab error down to acceptable for at least what they do. Or if you use a sectoral splitter, then you can use 10 grams. Our default now in the past has been 10 grams. They're insisting on 30 grams. They're trying to get it plus or minus 5% error in their data. They're looking for gold and such in soil or crushed rocks. 30 grams is ideal. Right now, we're still allowing 10 grams. But if your lab can do 30 grams, you should get the lab to do it. You'll get much better data. That's section 3.7. Go to Appendix K for more details. In section 3.8, goes through the data quality evaluation process. This says Appendix E. It should be Appendix L. So I'll fix that in the slides we post to our webpage. But here, you see, this is something useful, and talking with a lot of consultants here I've worked with, it goes through a step-by-step process of how to assess how good your data are. Now, laboratory or with sample data, what we focused on in the past has been data validation. You always get validated data or you can't use it. Well, that's at the very end of the process. So data validation just tells you how well the laboratory equipment was working when they tested the samples. Well, you need to start from the beginning when you're evaluating how useful the data are at a site. And that you start with were the DUs designated appropriately, then were the samples collected appropriately, were the samples processed and tested by the laboratory appropriately, and then did you collect or field replicate samples collected to test the precision of your sample data? So you go through all these, and only when you get a yes on all of these are you ready to go to your data validation. That's something we emphasize in here. And then once you get through this, Then you go on to section 3.9. The overview talks about, okay, now you have good data. How do you make decisions on it? So that was section 3. There's some other parts in there. Again, a lot of cut and paste from the original document with some additional useful notes added. In section 4 of the update now is the 17 appendices. And the idea here is you can go in and pull out your appendix, and it'll give you details on specific topics, use specific just for that. So Appendix A we talked about was fact sheets already. Appendix B talks about conceptual site models. Most of these are only 5 pages or so, maybe 10. So they should be generally fairly quick reads. Appendix C, this is a big addition we'll look at in a minute, talks about example decision unit designation schemes. This is really a compilation of all of our experience over the last 20 years, I think, on individual sites. We'll look at that in a minute. Appendix D goes into detail on the theory of sampling, what we now call infinite element particulate matter, like soil or in sediment and such. We'll look at that a little bit more detail in a minute. Appendix E talks about the use and misuse of discrete sample data. We added some notes on what we're talking about, referred to as contamination zones, A, B, and C, where A is everything's clean and sure you can test a pinch. I'll give you a correct answer. C is everything's dirty. Maybe a pinch works there also. But B is where it's kind of mixed. One pinch is clean, one pinch is dirty. That's where you really get into trouble using discrete sample approaches. Then appendix, F, G, H, I, J, they'll look pretty similar. Collection of surface soil samples, subsurface soil samples, how to test excavation and stockpiles, collect samples for VOCs, methanol and alternatives and such, collection of sediment samples. We've added some notes to these on what types of tools to use and just sort of tips in the field, but that's going to look fairly familiar. Appendix K, laboratory processing of multi-increment samples. That's also pretty much the same. There's a discussion there on the subsample mass and the need, if you want to get really good data, to bump the subsample mass up to 30 grams, not 10 grams. So think about that. You've got some area, maybe it's a soccer field. You're doing an exposure assessment. Does the concentration of lead in the soccer field exceed potential levels of concern, say 200 ppm? Well, how many cubic yards of soil are in a soccer field? It's quite a bit. That way, you're probably looking at tens of yards. And you're trying to get that down to a few grams of soil that the laboratory is going to analyze, and it's supposed to be representative of that soccer field as a whole. That you can get it down to 30 grams is pretty amazing. 10 grams, you're starting to push it. Standard methods now, EPA methods for metals and such, is 1 gram. And there's just no way that's practical, either to get a representative sample in the field down to 1 gram. So that's discussed more in section K. In section L, Appendix L talks about replicate sample collection, data quality review. We'll look at that in a little bit more detail. And then M is just some more field tips. So keep sending those in, ideas that work in the field, ideas that don't work in the field. And then Appendix N, common investigation errors and problems. Again, more kind of field tips. O is still in there. Appendix O, DUMIS investigations under TSCA, which my understanding now is some US EPA regulators are requiring multi-increment samples, or ISM, if you want to call it that, for investigation of PCB sites. The realization that your discrete sample data just aren't reliable for a site. Appendix P, clean field guidance, and then references. That's section 4. Now, I'll just hit a few highlights here. Appendix B talks about conceptual site models and data needs, and Appendix C, decision unit designation. This is something I've come to a better understanding over the last several years for. You're looking at systematic planning process, just comparing apples and dirt. And actually the whole approach applies to both. It's pretty much the same thing. Steps 1 and 2, prepare a draft conceptual site model and formulate a specific investigation question. You always need to have this in your pocket when you go out to a site to collect samples. In this case, this is a generic question that's common to most sites. Does the concentration of contaminant X in apples or soil pose a potential long-term chronic health risk? It's the same question, regardless of what you're dealing with. Steps 3 and 4, you identify data needs and designate decision units for sample collection. So In this case, you want to obtain pesticide data for the specified DU volume of apples or the specified DU volumes of soil. You're also only looking at the edible parts. So for the apples, you probably want to take the core out. For the soil, we're focusing on the definitely less than 2 millimeter particle size. Some risk assessors want to focus on the less than 250 micron or even 150 micron particle size, the edible parts, whether it's apples or soil. In step 5, you develop your decision unit statement. It's before you get into the field. If the concentration of contaminant X in the DU, apples or dirt, exceeds the action level, then the media must be disposed of. So you go through this process, and sure, it takes a little bit more time up front, making decisions on what your question is and designating decision units. But now you go out, you collect the sample, you get your data back, you look back at your decision statement, and you know what to do. It's not so much back and forth, remobilizing to go out in the field and debating what to do with the data. So that was Appendix B. There, Appendix C now is example DU designation scheme. So looking at this, if you've talked to me in the past, you're probably going to see notes that I stole and ideas I took from you and the sites you're working on. You know, not just in Hawaii, but in the mainland US, China, Vietnam, Australia, any other places where I've talked to people, and just really packed into here. It's supposed to help you get started at a site. So the first is one section discusses how to designate DUs for commercial industrial sites. And I really focus on DUs. Most people do in the field because you're collecting the samples secondary. We know how to collect the samples now. It's the biggest part in the field is how do you split this site up for testing. So for commercial industrial sites, there are case studies on how to deal with small spills. Just because it's small doesn't mean you go back to discrete samples. Same thing, 50 increments, 2 kilogram sample, or send all the dirt to the lab if it's that small. As this example of power plants, chemical mixing and storage areas, case study of a hotel redevelopment. There's an example of how to designate DUs at single family homes, high density housing, schools, examples for large single-use areas, former golf courses, former agricultural fields, and then for examples for very small areas, just area around a drum, a leaking drum or something. How do you test that? And examples for subsurface decision units, subsurface investigations. So you have a buried waste pit, or you had above ground storage tanks, but they've leaked and now there's a lot of contamination underground you have to deal with. And examples for stockpiles. Should add in excavations. Haven't done that yet. Then is the example for building demolition. This is getting me a bigger issue. Don't knock the building down before you test it. Lesson number 1, get the sample first. So how to test concrete structures and then concrete and asphalt pavement. Also sweet material and testing subslab soil under buildings as needed. This was actually some examples from the mainland plus what we have here. And how to deal with large industrial complexes. It's what I've been working on in China. And they're huge. They're square miles, square kilometers. How do you deal with that? Split it up into DUs. One lesson we learned here, which I've talked about in other presentations, you start off with one DU. The entire complex is one decision unit. Then you get your risk assessors and your remediation people there, and you start working from that. Most of them aren't going to be happy with that. So you start splitting the complex up into smaller and smaller areas until your risk assessors are satisfied with the data that should come out and your remediation folks are satisfied this what you have will help optimize remediation. You have examples on petroleum releases, crude oil pipeline release. It's an example from Minnesota, I believe where it was. And all these I kind of elaborate on, embellish it a little bit to make a useful case study. And then active gas stations, how to test those. There's one for gas station closure when the gas station's gone and how do you test it to close it, clean up what's needed. And then last on sediment decision units. So examples from drainage canals, wastewater outfalls, transformer spills. This was into a stream on Molokai. Looking at estuary, wastewater, discharges of contaminated sediment, harbor dredging. We need a fact sheet on that, or at least or separate guidance maybe on that. That's gotten to be a big issue. And then if you look on the bottom left, future additions, yeah, excavations, especially around USTs, they need to add some more details on that. But now we're dealing with in California, other places too. How do you test fire impacted areas? That's actually the case study I want to go over in a minute. So that's lots of information packed in there. I think it should be very useful. Appendix D, it's getting to be one of my favorite subjects, is the theory of sampling. So this one's expanded, like how did this idea of multi-increment sampling come into play? And it discusses the early mineral exploration industry. We have some webinars posted on this. In the development of Piaget's theory of sampling, they were trying to get down to plus or minus 5% error, say on what's the mass of gold in this 20,000 ton of ground up rock? Is there 100 kilograms, 105, or 95? They have to get down to that level of error in the mining industry. That's why they developed this theory of sampling and such detailed ideas of how to collect multi-increment samples. That's all discussed in the origin and nature of multi-increment sampling methods. And then there's a discussion on how this is applied to the environmental industry. The question has come up, and I've been to several conferences now, international conferences, why is the mining and the recycling, the agriculture, pharmaceutical industries, they're 50 years ahead of the environmental industry in a lot of cases. None of them would ever collect a random handful of ground up gold ore or pharmaceutical drugs or dirt in a farm field and test it. Same thing with the recycling companies testing catalytic converters for palladium and such. They always been collecting multi-increment samples, at least for the last 50 years. So it discusses why that is. And ultimately, it comes down to money. And it's a lot of, you'll find out really quickly if you underestimate the concentration of gold in this crushed up gold ore you're selling to some smelter in Germany or something, which I've seen happen. So there's a lot of monetary incentive to get it right. And money and third-party confirmation, because someone will go back and test this. It doesn't usually happen in the environmental industry. So a lot of details here on compositional heterogeneity, which the mining sampling statisticians have down pat. And we think about 1 or 2 kilograms of soil in our tests that we do. They look at 10 times that, or maybe even tons of soil, and they actually look at what the shape of the grains are under compositional heterogeneity. It's part of fundamental error. What's the density of the drains? What kind of concentration are you trying to target to get to? They have a formula where they actually calculate the mass of sample you need to test to get down to some target error. There's also a description of distributional heterogeneity. So instead of heterogeneity between individual particles, now we're looking at heterogeneity within individual areas within a decision unit. This could be something the size of a 1,000-acre farm field, or it could be the size of this sieved sediment or dirt sitting on a laboratory table, and how they collect a representative subsample of that. So that all falls under distributional heterogeneity. We'll give a more in-depth presentation or webinar on this sometime later. So that's Appendix D. If you really want to know how to collect samples of particulates, ground up rocks or dirt or pharmaceuticals, recycled catalytic converters, whatever, then if you got the time and money to spend, then the next World Conference on Sampling and Blending is in Johannesburg, South Africa in May 2024. I've been to the last two. The first one was in Beijing, China. And then last year there was one in Norway. What a great group of people. And these folks write books that most people, including myself before, had never heard of in the environmental industry. Like a sampling of particulate matters and such. So I've been invited to that. I doubt I'll go unless somebody is going to pay for it. But I'm on the review committee for reviewing some of the documents, the papers that get submitted. Really fun group of people, pretty intense. So I should say Appendix D here. The last notes on DU characterizations, and we know how to designate our decision units. That's a big deal. How do you collect a proper sample? So under systematic planning, now we're down to steps 6 and 7, where you develop a sampling analysis plan, and then you collect a sample that is representative of the decision unit designated and the investigation being asked. So if you're worried about pesticides in apples, say this batch of apples, you suspect one of them might have high concentration of pesticide. Each different type of apple is its own decision unit. You're not going to just grab one apple from each one and test it. You're not going to grab 3 or 4 from each one and test them independently. The question is, do the apples as a whole, we're looking at chronic health effects, pose a potential health risk? So you're going to go to each group of apples and you're going to collect a representative sample. Well, how many apples should you collect to be representative? Well, you have to run tests on that. That's what they would do in the Food and Drug Administration when you're testing produce. You actually run tests. They're going to collect 10 and 20 and 40, 50, 100. And they'll do replicates each time, and they start comparing the data until the data start to look fairly consistent. Then they know that's the right number of increments. Same thing for soil. We know from past experience, and definitely working with the mining industries and agriculture industries, such that once you get up to about 50 increments of soil, so you collect one sample from about 50 points, that sample weighs at least 1 to 2 kilograms, then you're going to get fairly accurate data. And you'll go back and test this anyway. One of these DU areas here, like I have outlined, 10% of those anyway, you'll go back and do it 3 times and compare the data. That's what consultants here in Hawaii and other places have found. 30 increment samples, the precision of your replicate data can be pretty far off. It's always surprising, but it happens. Once you get up to about 50, then you can be fairly consistent. That was it. And there's a discussion of discrete samples, use and misuse in Appendix E. Well, that's the same things. A discrete sample is just a random handful of dirt collected from one spot, and then you send it to a lab. They open the jar and test a random pinch of that. Laboratories, you can't homogenize soil. So one lab chemist told me, try sticking a metal rod in a jar and stirring. It doesn't work. If anything, all the fines go down to the bottom where the contaminants are, and they grab a pinch from the top and test it. So your data can be really unreliable. Sample in the field, you move it over a point or two and test it, and you can get a completely different number. And that's not surprising. We've always suspected that in the field. We demonstrated this now in some field studies we have posted to our web. So instead of collecting 9 discrete samples at this site, this is actually a milk truck, but it gave good examples, I think. We talk about that in our webinars. And you find all these isolated hot spots and such. It could be totally fake. You'd split the site up based on what your question is. If this was a soccer field and the question is, does the concentration of milk in this soccer field or lead pose a potential health risk? Well, the whole area is one decision unit. You collect one sample from it, from at least 50 points. Do it 3 times. You'll pick up the average concentration of milk in this area. If you're trying to optimize remediation, you know you already have a spill, you'll split it up into smaller decision units and collect a good sample from each one of those. And then you identify areas that need remediation to reduce your risk. Let's discuss more in Appendix E. Then that was Appendix 4. Then it's the 17 appendices, been through those. I'm not going to go through the others. A lot of them are surface soil, subsurface, and such. They're all kind of cut and paste from the original guidance and elaborated on in some cases. And we've added to field tips and such. And there's a more extensive data on data quality review, including a checklist that you go through. Check off, was the sample DU designated properly, was the sample collected properly and processed properly and such. And then the last thing you look at is data validation that the laboratory's equipment work right. So in the future, I think we can give focused webinars on each one of these topics. But what I want to end up with now is a new case study. It's not in the guidance, but this is the assessment of fire impacted urban areas in Maui. Quite a tragedy that was. We've got a lot of experience. Thank you, folks in California who, at least the lemon part, I guess lemonade part of the lemons there in California, they've helped us quite a bit on understanding how to deal with fire impacted areas. But it's the same process, and it is really difficult to wrap our arms around. We start. It reminded me of some of the industrial complexes I worked on in China, where they're just huge. Like, how do you even begin to test this? Well, you start with the same type of questions, the systematic planning process. The question could be, this is what was actually asked to us, is do contaminants in fine-grained ash and soot, which I'll just call ash, pose a potential health risk to workers clearing fire-related debris throughout the residential and commercial areas? So right now, the Army Corps of Engineers and their consultants are going through each one of these lots one by one and clearing the debris. So of course, there's some concern, what's in this ash, especially the fines that get airborne that could be inhaling or getting on their skin and such. Second question, at the top of this photo here, this is Lahaina, the schools, which weren't impacted by the fire. The question was, they're going to reopen the schools this month. Well, do contaminants and potential airborne dust from fire-impacted areas pose a potential health risk to residents and students and staff in the surrounding areas? This ash is blowing up in the air, so that's the second question. And you can see in the photos on the right just how complex individual lots where these houses and commercial buildings burned is. So how do you start this? Well, first thing, what are our contaminants of potential concern? Primary concern, we knew ahead of time, are the heavy metals, especially arsenic and lead. And you also polyaromatic hydrocarbons, pHs, you're going to get in burn material. Dioxins and furans, the same thing. Other potential contaminants of concerns, you see pHs, heavy oils. Somebody wanted us to test for PFAS because they're in fire-resistant carpet and furniture and such. Another group wanted us to test for flame retardants, polybrominated diphenyl esters, and organophosphates and esters. There was concern about asbestos in the material also, even though EPA emergency response people are going through each one of these lots one at a time now and removing any obvious asbestos along with propane tanks and things. And there's also concern about organochlorine pesticides because a lot of the lots were treated for chlordane for termites in the past. So step by step, here's our contaminants of potential concern. Okay, we have those. What are our decision units? What's your decision unit? Well, again, go back to your questions. What's the question? So the first question was concerned about exposure to workers to the ash. They're going throughout these entire areas. Second question, concerned about exposure, offsite exposure to airborne ash. So what's our decision unit? Well, we have residential areas and commercial areas. So the ash might be different in each one of these, but our decision unit is all of the ash, which here we're defining as less than 250 micron particles within that targeted area. So you see this residential area, DU1, it's about 400 or 500 homes. It's around 100 acres. Our decision is all the ash in that area. DU2 is the commercial area, which actually we're probably not going to get access to test that, all the ash in that area. What's the ideal sample? It'd be to let's collect all of the ash in each one of those areas, 2 separate samples, and send that to the laboratory for testing. Of course, you can't do that. So we do the next best thing. We get a representative sample of that ash, 1 sample of the ash in each one of these areas, each one of our DUs. That's our DUs. Also, as concern up in Kula, this is on the side of Haleakala. This one, there are a lot of discontinuous areas of burned houses, about 25 or so. So one house might be fine, house beside of it completely gone. You can see here on the right. We were out there 2 weeks ago collecting samples. So what's the DU? It's all the ash collectively from these homes together. Say if a worker was going out lot to lot, where you see these red circles being exposed to the ash, our decision is ash in all these together. It's ideally, again, we collect all that ash and put it in one big jar, bag, and send it to the lab. Can't do that, so we have to collect a representative sample of that ash. That's how DUs work. We had to keep this in mind in the field. And you see, now we have to go out and collect a sample. And you see these question marks and stay focused. Those are kind of notes to self. Because when you get out there and start looking at these burned house lots, there's so much there. And there's, what do you test? You start thinking, wow, could this be hazardous? Could that be hazardous? How about looking at TCLP for disposal in laboratories? Well, that's not the questions. You really have to stay focused on the questions. And again, this is what I'm telling myself. A question only deals with the mean concentration of these COPCs in fine ash from the combined lots in the Kula, these house lot areas. So how do we get a sample of that combined together? Well, we went to each of 8 house lots where we had access, and we wore Tyvek and steel shank boots and half-mast respirator and such. We had a small 2 tablespoon scoop, 30 milliliter scoop attached to the end of a Swifter rod, like you clean floors with. And 3 of us would go up to a house lot, and we were going to collect a 30 increment sample, or we're going to collect 30 of these 30 milliliter 2 tablespoon spoonfuls. Each spoonful would have been an increment. So 3 of us went there. Each of us collected 10. We kind of randomly wandered through the areas, did that. So we got 30 increments from each house lot of 8. So in total, we collected a single 240 increment, 3 kilogram sample of the ash. So all this will be combined into a single sample for testing at the laboratory. They're going to, they're going to air dry it, process it, and then they're going to test minimum 10-gram subsample of it for all our COPCs. So that worked pretty well, but I have to say it was hard, especially for me, I think, to stay focused in the field. But in the end, we got, I felt like it was a really good sample. And then the laboratory again, air dry it, sieve it, spread it out. They're going to collect a subsample, test it, minimum 10 grams. Be nice to get 30. It's not going to happen in this case. And for some of the samples, actually for all, this is one sample, they're going to test the same sample 3 times for metals, pHs, and dioxins, so the kind of 3 contaminants are concerned. And that'll tell us that the laboratory is collecting a good subsamples. We didn't collect replicate samples in the field because once you get over 100 increments, we just know from past experience, it's really, that's about as good as you can do. We collected a 240 increment sample. There's really no need to collect increments. If you can't get a good sample with 240 increments, then that's a problem you can't really solve in the field. That's the laboratory processing. We had the sample back at our office. We have a portable XRF, so we shot the sample with the XRF just to get some ideas ahead of time what might be in it. And it turned out that first thing you notice is the arsenic was really high, 700 ppm just in this shot. That's probably average, maybe a little bit lower, but definitely hundreds of ppm. Some of the XRF shots, and the XRF is testing about a cubic centimeter of this ash. Some of them were in the percent level, 2%, 20,000 ppm arsenic. We know, and we knew that some of these older houses use something called canic. It's arsenic infused sugarcane waste that they use made wallboard out of, but even that was really high. So we were wondering at first, wow, where is this from? Then we scrolled down on the XRF and we saw high copper, high chromium every time we saw high arsenic. So it's kind of a duh moment, but it was. We were looking at a burned CCA wood, ash from it. So I'm sure we're going to get some moderate levels of dioxins in here. There's hardly any lead, but arsenic's going to drive risk. Here's the XRF analysis. So that sample here, this is just one shot I'm showing. See, arsenic 741 ppm, but then copper, chromium were high too. And if you look at the typical makeup of copper, chromium, arsenate treated wood, this is all the, the walls and the floor and the roof of the building, which is going to make most of the ash when it burns. Then it fits in pretty well. Copper was a little bit high compared to how CCA treatment is usually done, and we suspect this could be, it's just from a few XRX shots. It could be some of the copper wiring in the walls that was mixed in with the ash. So it's a useful experience, a terrible tragedy. Hopefully we can learn something out of it. Again, it's not the lead in this case, it's driving risk. And I bet you see this in a lot of fire burned areas, it's going to be the arsenic. Behind us, same thing. There we've got our DUs. We're scheduled sometime this month to go out and collect a sample there. Well, how do you collect one sample from 100 homes in 100-acre site? Luckily, we've done a lot of work in sugarcane fields, so we've done this before. In this case, there are about 400 homes. We're going to go to 100 of the house lots, the burned lots. We're going to collect a single 100 increment sample, about 3 kilograms. Again, the same before. Each increment in this case is going to consist of 3 30-millimeter scoops from a single lot. So you see the red dots here, the white diagram up first. We spread the 100 different lots we're going to collect a sample from. They may not be these exact ones, but you get the idea. More kind of semi-systematic random fashion across the area. So it should be a pretty good sample. Again, each lot, 3 scoops, 30 millimeters, so get about 90 millimeters of ash. That's going to be a single increment in this case. Schedule sometime later. How are we going to do that in the field? It's a big area. It gets really hot, especially if you're in Tyvek. We're talking about having 2 or 3 sample teams, and they would just wander, say on the yellow path, they walk up and then back down. That's going to be about a mile total. As they're going up, they'll just go alternating every 4th house lot, and collect an increment from that, put it in their bag, have a bucket, go to the next one, put that in the bag in the bucket, and have maybe a team going up the purple area. They're going to walk up through the area, come back down. They'll have their 1/3 of the sample. Then the same thing with blue. Then at the end, all that will get put together. Probably leave it in the individual bags, but send that to the laboratory as one sample for testing. So we'll see how that works. I think we've got some good experience with it. So that's it. Quick overview, quick case study. I think I'm glad we had our guidance in place before they sent us out to Maui to collect samples, because it really required a lot of systematic thinking and planning ahead of time. So Last thing that I want to talk about is just ideas for focused webinars and discussions, and start incorporating more guidance and modifying some sections as needed. So just some topics to think about. An overview I think would be useful for people who don't want to get into all the details. We don't need a 2 or 3 hour webinar, just maybe a 45-minute webinar, which is the general overview of how this whole risk-based investigation process works. And we still have to keep going back, I think, and talking about use and misuse of discrete sample data. That's still an issue. One issue in China, they'd started copying EPA's guidance from 30, 40 years ago. Some of the sites there, at least initially, were a total mess. We've got those back on track, I think. And I think giving some case studies, going through this example of BU designation schemes for different types of sites would make a really useful webinar, kind of focused. I like to give a webinar too on the theory of sampling and infinite particle matter testing, and why multi-increment samples were developed, how they work. And we can give additional webinars on collecting of surface, subsurface samples, VOCs, excavation stockpiles. I think in reality, the webinars we did in 2017 cover this pretty well. Could have a webinar on pavement and building demolition debris. I like to do that just to get your ideas for putting together fact sheets. And sediment samples, same thing. We have webinars posted from our 2017 series, but we can have separate webinars on that. And same thing for laboratory processing. One idea I had for these specific topics, if we do want to talk about surface sampling, then I can give a brief overview of that, but maybe we can get someone to come in and give a case study that we can talk about. So that's it for this overview of our edits. Any suggestions, questions you folks have, be glad to take. This is the evergreen document. So we'll be editing this for a time in the future. So with that, Vicki, if there are any questions that come up, I'd be glad to answer, discuss them.
Thanks, Roger. Let's see if there's anyone no one's put a question in the chat yet.
All right, we all have it down. While you're looking at that, so what I'll do now, I'm going to be traveling quite a bit in the next month or two. But after that, then at some point, I'll start going down this list and having some focused webinars I can send out. If you have any ideas for some specific topics you want to discuss in a webinar, then send that to me and we'll get it on the list. Again, these are maybe fairly short. Yeah.
Oh, I see we have one question.
Okay.
Are labs still allowed to use 10 gram for subsamples for organics?
Are they allowed to? Yeah. I mean, for now, we'll still use 10 grams until labs can increase it. I think for some contaminants, they're actually still already doing 30 grams, but we'll still keep doing 10 grams. But if you're getting your laboratory replicate sample are pretty far off for some reason, then that's the next thing you need to do is increase the mass that the laboratory is testing. And bump that up to 30 grams and you'll probably start getting better precision in your laboratory samples. But for now, it's ideal, but to scale up to 30 grams, for things like PFAS now, the EPA's default lab methods call for testing half a gram, which that may work fine from a chemistry standpoint, but it's pretty ridiculous from a field standpoint. There's no way you can test half a gram of particulate matter and it be representative of the sample you collected physically. So for that, the laboratories are testing. They can test 10 grams for PFAS. You're going to pay a little bit more because they have to spike it with isotopes. Additional isotopes. It might cost you $100 more, but that's what the cost is to get real data. If you're testing biosolids and stuff, a lot of organics, they can only test 5 grams. So we just have them do replicates in the laboratory, get an idea of how good the data
are. Another one, Roger, to what degree is the EPA supporting MIS sampling?
That's a good question. And there's some people in EPA. I gave a first presentation to EPA on our guidance, and I think it was 2009 in San Diego to a bunch of EPA project managers. And I was ready for a fight at the end of it. I like to debate in a good way, I like to think. And there were no questions. And the guy in the back stood up, Craig from Region 10 and said, Roger, we've been trying to get this going in EPA for 10 years. So, and there, Region 10 especially has been doing multi type sampling for years. And there's somebody from all the other regions, but it's real varied. And then it's, it's new to some people. I think the problem has been that there just hasn't been good guidance out there. And even our guidance, it was good, but it's good if you already know what you're doing, as somebody said. So hopefully this will help get it going. ITRC's guidance, we gave a presentation on it. We gave a critique of it, and the introductory parts of that and problems with discretes, how to collect MI samples, and the field work are pretty good. But there's some problems in there on the risk of how to assess risk, and the sampling discussions just don't apply to soil and such. So I think that's been one of the main problems getting EPA on board overall. But certainly the Superfund office in DC has been giving webinars on it and such. It's a slow process, but they're getting closer on board. And as I said, some of the TSCA people I know are requiring MI sampling for TSCA sites now for PCBs.
Yeah, someone did note that several EPA regions are implementing it within many programs. So it sounds similar to what you're saying. We do have one more question. So method 1633 allows for 5 grams of sample. Will that remain acceptable? And how many replicates are required for that?
Well, for 1633, then they could do 10. That's great. They bumped it up to 5 from 0.5. So it's still, if you start doing laboratory replicates, you have the laboratory test the same sample 3 times. With 5 grams, you're going to start seeing higher differences between your data, your samples. So your relative standard deviation could be over 35, or especially over 50% or something. So then what do? You have to tell the lab to go back and test it again and collect a bigger mass. So it's kind of like in the field, how many increments should you test? We try 30, sure, that works sometimes, but what do you do? And that you blow your replicates, you have to start over. So tell the lab to do 10. They've been doing 10 for us routinely. You just have to pay a little bit more.
I don't see any more questions in the chat.
All right. And one thing too with EPA, just jump back on that. So who's driving all this? And I talk about this all the time. I discuss it with my coworkers, friends in California, especially, is the labs in California they're overwhelmed with multi-increment samples or ISM samples. But there's not a single agency in California that has guidance or it requires it that I know of. So who's pushing this, and who's going to push the regulators to make the transition? Then it's the attorneys and the people giving out loans on these huge redevelopments. They're the ones that get burned if they're in the middle of a project and suddenly discover contamination that shuts everything down. So they're, as much as we harass attorneys, they're the ones in the banks and all, they're the ones that are pushing this along. And they're actually the ones pushing it along in China, because there's a lot of money spent on cleanups and redevelopment of sites there. And there's a lot of NGOs and environmental attorneys now in China. But if there aren't any more questions, then you have my emails on the front slide. I saw a few typos. I'm going to repost the slides, and then we'll hopefully have a recording we can post to our YouTube station. If well, we will have one sometime later on this week or soon. But send any other questions and ideas, future webinars to me. And thanks again for all the help on getting this guidance going over the last 20 years now, especially the last 15. So with that, no more questions. Thanks again. And
Thank you, Roger. Thank
okay.
you, Lauren, for helping with the questions.
All right. Thanks, everybody.